So we employed density functional theory investigations and artificial intelligence in order to identify descriptor for ion mobility. And after that, we tried to search in periodic table to find new elements that can help us in order to improve magnesium mobility in some frameworks. And finally, we also synthesize materials in a lab. So these are the methods that we had. So the sluggish kinetics of magnesium in frameworks such as spinel, especially oxide spinel, was a challenge, a big challenge. And for us, it was a primary topic to invest time on. And this was a big challenge for us, and we tried to use computer and try to use artificial intelligence, and also try to search for different material and different chemistries and propose a new material in a lab. So our finding is that electronegative elements such as rhodium or iridium, both they show a very good mobility when we dope them into the spinel oxide. So imagine we replace transition metal with rhodium, and then you have better mobility for magnesium. So it improves the cathode functionality for us. And we also used a theoretical calculation in order to analyze the stability of the compounds. Interestingly, we found that iridium doesn't show any stability in a spinel framework, while rhodium it shows. And this is something that we prove in a lab, that we can synthesize a spinel structure with rhodium, while for iridium we are not able to synthesize that, and it forms different compounds. Yes, we also test our understanding in a lab, and we had a very good agreement between the theory and experiment. So in a lab, as I said, we try to synthesize materials. Of course, we need to go for the larger scale and put material in a, let's say, in an electrochemical cell, but we synthesize material, and we were successful in order to dope rhodium into the spinel structure with different content. For example, with from the 0 to 0.5, let's say, doping, we were successful, and we also used the XRD pattern, and we find that without changing crystal structure, we can synthesize this material. So our idea is to continue to analyze and also to optimize the materials and the cathode functionality with respect to the theoretical findings that we had. And we want to investigate this idea to other class of the materials and also other battery chemistries that we are working on here. So, and at the end of the day, we also have a plan to go beyond crystalline solids, to spend time a little bit on an electrolyte phase, and to apply these understandings to a broader range of the materials. The future plan is to, because we synthesize this material and now we want to put them into the electrochemical cells, and we are optimistic because it's challengeable. Maybe we have some instability, some solid electrolyte interface, but the future plan is to use this material in a realistic situation as a battery and try to see how it works for us. And if we were successful, the future plan would be to scale up production of this material for having the first, let's say, applicable magnesium batteries.